Hello everyone, my name is Siti Izzatul Akmal binti Zaidun. Today my group will present about Maxwell equation. In this video we will explain about the introduction of Maxwell equation, first Maxwell equation, second Maxwell equation, third Maxwell equation, fourth Maxwell equation, and also the application of the Maxwell equation. Maxwell equations are a set of four complicated equations that describe the world of electromagnetics. These equations describe the electric and magnetic fields arising from distribution of electric charges and currents, and how those fields change in time. James Clerk Maxwell, a Scottish mathematician and physicist, published a physical and mathematical theories of electromagnetic field. Maxwell was a true genius who made several contributions to the scientific community, but his most important achievement was his development of the equations of electromagnetic waves, which now we know it as Maxwell equations. Maxwell's first equation is Gauss' law, which dictates how the electric field behaves around electric charge. Gauss' law states that the total electric flux through any closed surface is equal to the total charge enclosed by that surface. Gauss' law can be written in terms of the electric flux density and the electric charge density, which is delta dot T equal to rho V. This equation is known as Gauss' law in point form. That is, this equation is true at any point in space. If there exists electric charge somewhere, then the divergence of T at that point is non-zero. Otherwise, it is equal to zero. To get some more information on Gauss' law, let's look at the Gauss' law in integral form, which we integrating the equation, the first equation, that in point form into the integral form, which we get this. So the Gauss' law in integral form states that the amount of charge inside a volume V is equal to charge enclosed is equal to the total amount of electric flux existing the surface S. To determine this electric flux leaving the region V, we only need to know how much electric charge is within the volume. So we can rewrite the Gauss' law in integral form with more of in terms of defined in the next equation, which is we get like this.
Hello, my name is Nur Ainatika. Now I will be presenting to explain about the Maxwell's second and third equation. Maxwell's second equation. Maxwell's second equation is form of Gauss' law and only with magnetic flux instead of electric flux. The magnetic source always dipoles with north and south pole. Magnetic field line lead from the north pole and to the south pole. As you can see, magnetic field interact with a surrounding surface. You see that the field line flow out of the north to the south pole path through the surface. So this equation does mean magnetic flux is being zero. Compared with the first equation, the integral of magnetic field over the surface area is the same, but the integral will always zero for a closed surface. Now we go to the Maxwell third equation. Maxwell's third equation is form of Faraday's law. Faraday's law of induction is that a changing magnetic field will inducing an electromotive force in a load of wire. Maxwell is version more general. Faraday's law to show the value of induced EMF. EMF is equal to the line integral of the electric field over a closed loop. This equation is connection between a changing magnetic flux and an induced electric field. For the first and second equation will grow similar, one for electric field, another one for magnetic field, which is it must be an equation complemented Faraday's law as well.
Hello everyone, my name is Idham bin Zana Arifin. I hope you guys informed about the Maxwell equation and what are they used the equations for. So today, my mission is to complete the missing piece which to explain the last equation in the Maxwell equation, which is this one. This fourth Maxwell equation is actually incomplete. Why? Let's look at this circuit. If we take the line here, the integral of h.dl is equal to the current of the circuit. But what if we take the line here? The integral of h.dl here is actually equal to 0. But we know that in the circuit, at that line, there is still a current flowing at that part. So that is why this equation is actually not complete. The hypothesis is that del cross h is equal to j and then plus with jd, which is the displacement current, and this jd is equal to del d over del t. And let's prove that. So del cross h is equal to j plus jd, and we get that del dot del cross h is equal to del j plus del jd. And like what I mentioned before, del cross h is equal to 0, and we get 0 is equal to del j plus del jd. We arrange the equation and get del jd is equal to del j. So del jd we know is equal to del rho v over del t, and we get this one. So rho v is equal to del dot d and leads to this. Last but not least, we get del jd is equal to del d over del t, and we cancel the del on the both sides, and we prove that the jd is equal to del d over del t. The last part in this Maxwell equations is the application of it. There are several things that included these Maxwell equations, and some of them are in our daily basis. We know that Maxwell equations are related to electricity and magnetism, or simply I can say the electromagnetism. One of the application is the antennas, which used to receive electromagnetic signals. And Maxwell equations help the system to work perfectly. Other applications which included the Maxwell equations are in the transmission lines, the MRI scanners in the hospitals, the electricity generation, and the one I said which in our daily basis is the ceiling fan capacitor. This ceiling fan capacitor included this displacement current, or the JD, and the introduction to the Maxwell equations. Those are some applications which related to Maxwell equations.